It began as nothing more than a faint, thin line in a patch of sky no one had thought to watch closely. A small movement, barely distinguishable from the background noise of stars, crept across the night. Telescopes caught it by accident, just a smear of reflected sunlight drifting in the dark. At first, astronomers thought it was an ordinary asteroid passing through our solar system. But as the data piled up, that easy explanation began to slip away. This was something stranger, faster, and far older than anything we had ever seen. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And tell me where you're watching from, along with your local time. It's always fascinating to see our little community spread across the globe. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. On the morning of October 19, 2017, the Pan-STARRS 1 telescope perched on the slopes of Haleakala in Hawaii was running its usual survey of the skies. Its wide-field camera scanned for asteroids and comets that might pose a threat to Earth, a daily ritual in the quiet but relentless work of planetary defense. That day, something unusual drifted into view. It was moving faster than expected, slicing across the field of vision in a way that hinted at an orbit unlike any other. At first, no one paid much attention. Strange orbital paths can belong to oddball asteroids or comets tossed inward by Jupiter's gravity. But when astronomers calculated its trajectory more carefully, a ripple of excitement and unease spread through the community. This object wasn't looping gently around the sun. It wasn't bound by the familiar paths of the planets. It was on a one-way journey. Its track cut sharply through our solar system like a needle through cloth, with no return. The realization was unsettling. This was not a native of our cosmic neighborhood. It had entered from deep interstellar space, a realm so vast and so empty that crossing it takes millions of years, and it was already leaving. Astronomers had stumbled onto the first recorded visitor from another star system. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first. That name carried a weight that matched its mystery. Oumuamua had slipped past the orbit of Mercury, brushed near the sun, and was already racing away before we even knew it was there. Its speed, over 315,000 kilometers per hour, was far too great for the sun's gravity to capture it. This was a brief encounter, like a ship glimpsed on the horizon, already vanishing into the mist. What made it even stranger was its silence. Many comets visiting from the icy edges of our solar system brighten dramatically when they swing near the sun, their ices vaporizing into glowing tails. Oumuamua did nothing of the sort. No gas, no dust, no bright coma. Just a silent, dark object, tumbling through the sunlight as if it had no interest in announcing its presence. As the first images came in, they revealed something unprecedented. Oumuamua's brightness fluctuated wildly over hours, suggesting it was not round, but stretched into a bizarre, elongated shape, perhaps 10 times longer than it was wide. No asteroid or comet ever seen in our solar system matched such proportions. It was like finding a splinter where you expected a pebble. The discovery rippled beyond the observatories. News outlets picked it up. Headlines spoke of alien visitors, and for the first time, ordinary people around the world were hearing the name Oumuamua. But astronomers knew the reality was both stranger and subtler than the easy headlines. This was no ordinary rock, no familiar kind of space ice. Whatever it was, it had been traveling alone for untold millions of years, wandering between the stars before its brief and accidental meeting with us. Even in its silence, it whispered of vast distances and ancient origins. And as it slipped away into the black, the hunt to understand it began. For those who studied the cosmos, this was not just a discovery, it was a challenge. What was this messenger trying to tell us, and would we be able to listen before it was gone forever? The first whispers of Oumuamua's true strangeness didn't come from dramatic photographs or dazzling displays in the sky. They came from numbers. Cold, precise measurements of light, speed, and trajectory quietly began to paint a picture that didn't fit into any known frame. At the Minor Planet Center in Massachusetts, astronomers were crunching the initial observations from pan-stars alongside follow-up data from telescopes across the world. Every time they ran the calculations, the answers came back the same. This object wasn't behaving like anything born under our sun's watchful pull. Its orbit was hyperbolic, meaning it wasn't an ellipse like the paths of planets or comets, but a curve that opened outward. A track designed by physics to never return. In simple terms, Oumuamua had come from somewhere else entirely, passed through our solar system in a single sweeping arc, and was on its way out forever. The numbers suggested it had been traveling for millions, perhaps hundreds of millions of years, before fate brought it near us. And then came the other oddity. Astronomers expected that if this were a comet, it would release gas as the sun's heat warmed it, jets of vapor that would cause subtle changes in speed and rotation. But Oumuamua wasn't giving off the bright halo or tail of dust typical of comets. It remained stubbornly invisible to anything but reflected sunlight. To see movement without visible release of material was a puzzle that made even veteran scientists hesitate. The fluctuations in brightness became another quiet alarm bell. The object's light curve, a graph showing how its brightness changed over time, was unlike anything on record. The peaks and dips were sharp, uneven, and repeated in a pattern that suggested it was tumbling, not spinning smoothly. That tumbling motion implied a violent history, perhaps a collision or breakup in some distant system, long before it entered the dark between stars. As telescopes tracked it night after night, it became clear how fleeting this encounter would be. Oumuamua was already on its outbound leg, moving so quickly that every delay meant precious lost data. The most powerful observatories in Hawaii, Arizona, and Chile were scrambled to point their mirrors toward the faint speck. The European Southern Observatory's Very Large Telescope in Chile, one of the most sensitive instruments on Earth, joined in, its adaptive optics peeling away atmospheric distortion to get clearer readings. Even with the combined power of these instruments, Oumuamua was frustratingly faint. By the time its image reached us, it had been dimmed by 25 magnitudes, the equivalent of trying to spot a single candle flicker from thousands of kilometers away. For the scientists watching this drama unfold, every photon counted. They carefully measured the way sunlight reflected from its surface, hunting for clues about what it was made of. The colors hinted at a reddish hue, similar to many icy bodies that linger in the outer reaches of planetary systems. Red from billions of years of cosmic radiation, baking complex organic molecules onto its surface. Meanwhile, the urgency of the situation was becoming clear. Most astronomical discoveries have the luxury of time. A star can be studied for decades, a planet for centuries. But Oumuamua was already racing beyond Mars's orbit by the time most of the world even heard its name. Each night it slipped farther away, becoming dimmer and harder to track. This was a once-in-a-lifetime chance, and the clock was running down. The data arriving in those early days carried more questions than answers. Was this a shard from the birth of another star system, flung into interstellar space by gravitational chaos? Was it a fragment of a larger world, broken apart in some unimaginable catastrophe? Or was it something even stranger, an engineered object, drifting silently, its creators long gone or watching from an unthinkable distance? In astronomy, such speculation is usually kept quiet until the evidence builds. But Oumuamua's fleeting appearance left little time for the usual slow and careful process. The whispers began early, spreading through conference calls, late-night emails, and hallway conversations at observatories. The object's speed, its trajectory, its lack of visible outgassing, they all formed a pattern that didn't quite fit into any existing category. It was in these first days, as the global network of astronomers worked frantically to collect every scrap of light they could, that the mystery deepened. The shape, the motion, the color, the silence. It all hinted at something profoundly alien, in the truest sense of the word. And yet, even the boldest among them knew this was only the first glimpse. What lay ahead was a battle between time and curiosity, with the universe itself holding most of the cards. The truth settled in slowly, like dawn light spilling over the horizon. Oumuamua was not from here. The calculations left no room for doubt. Its hyperbolic trajectory wasn't just unusual, it was mathematically impossible for anything born inside our solar system. Its velocity at the edge of the sun's influence, what astronomers call the excess speed, was a clear fingerprint of an interstellar origin. Even if Jupiter or Saturn had given it the strongest possible gravitational slingshot, they could not have accelerated it to the speed it already possessed when it arrived. It had entered our neighborhood carrying energy from somewhere else, like a stone thrown from a distant shore landing in a still pond. That realization alone was enough to reframe the discovery as historic. For centuries, astronomers had suspected that chunks of rock and ice must wander between stars. Every planetary system is messy, with planets tugging on each other's orbits, hurling loose material outward. Most of those ejected bodies drift forever in the cold dark, never coming near another star. But statistically, some must pass close enough to be seen. The idea had been a quiet certainty for decades. Yet, until October 2017, no one had ever spotted one. Oumuamua was proof that the void between stars is not entirely empty. Its point of origin, however, was harder to pin down. By retracing its incoming path, astronomers hoped to link it to a nearby star system. The trajectory pointed roughly toward the constellation Lyra, not far from the bright star Vega, at least in our sky's perspective. But Vega itself couldn't have launched it. The star wasn't even in that part of space when Oumuamua would have passed by. Stars move over time, their positions shifting in subtle arcs. Going further back, astronomers traced the likely path across millions of years, but the distances involved blurred any certainty. Oumuamua might have begun its journey in a binary star system, where two suns orbit each other in a gravitational dance, or perhaps near a massive planet that flung it outward with a final, irreversible shove. Whatever the origin, its voyage was ancient. The space between stars is not only vast, but slow-moving. Even at tens of kilometers per second, it would take millions of years to cross from one star's domain to another. Oumuamua had been adrift for longer than human civilization has existed, perhaps longer than Earth's continents have held their present shapes. In that time, its surface would have been altered by cosmic rays, micrometeor impacts, and the slow erosion of space weathering, leaving behind a hardened shell that concealed whatever lay beneath. The knowledge of its age made its arrival feel almost ceremonial, as if it were carrying the history of another world within its core. This was not a messenger in the sense of delivering a specific message, but it was proof, undeniable and solid, that other planetary systems breathe, grow, and shed material just as ours does. For the first time, humanity could study a physical fragment of another star's story, not in theory, but in real light bouncing off its surface. Astronomers began to imagine what this fragment's home might have looked like. Perhaps it was born in a newborn system where planets were still forming in a disk of gas and dust. It might have been part of a planetesimal, one of the building blocks of planets, before gravitational chaos tossed it away. It could have wandered in the cold outskirts of its system for eons before a chance encounter with a massive neighbor flung it into interstellar exile. And all the while, it traveled in perfect silence, unchanging, unobserved, until it stumbled across our sun. The recognition that Oumuamua was a true interstellar traveler shifted the tone of the search. This wasn't just an odd asteroid or comet, it was the first ambassador from beyond our sun's family. Its value as a scientific target skyrocketed, and telescopes worldwide were reprioritized to watch it. Time on the world's largest observatories is precious, scheduled months or even years in advance. But for Oumuamua, schedules were torn apart. This was history in the making, and it wouldn't wait. And yet, as the excitement grew, so did the tension. It was moving too fast, fading too quickly. Each day meant a little less data, a little more uncertainty. The sheer brevity of the encounter meant scientists had to make peace with the idea that much of its story would remain out of reach. Still, what they did learn in those early weeks would change how we think about our place in the galaxy and prepare us for the next time a traveler without a home comes calling. From the moment the world knew Oumuamua was interstellar, the race was on to figure out exactly what it was. Every available telescope, from ground-based giants in Chile to the orbiting eyes of the Hubble Space Telescope, was pointed at the faint, darting speck. But nature was cruel. Oumuamua was already speeding away, dimming faster than most instruments could handle. In a matter of weeks, it would be too faint for even our most powerful tools to see. The first step was to understand its size, shape, and rotation. Astronomers measured how its brightness changed over time, creating what's called a light curve, a graph showing how much sunlight it reflected as it tumbled. That light curve was bizarre. Most asteroids have fairly gentle, predictable brightness variations as they spin, but Oumuamua's light curve fluctuated dramatically by a factor of 10. That meant it wasn't just elongated, it was extremely elongated, perhaps 10 times longer than it was wide. Some even suggested it might be shaped like a cigar, spinning end over end. Others thought it might be a flat, pancake-like shard, flipping as it traveled. Either way, its geometry was unlike anything seen in our solar system. Then came the question of composition. Was it rock, ice, something in between? Normally, comets tell us their makeup by sprouting a tail when they pass near the sun. Solar heat turns their frozen gases into visible plumes. But Oumuamua had no tail, no fuzzy halo, nothing that screamed comet. And yet, its motion betrayed something odd. Careful tracking revealed that it wasn't moving exactly as gravity predicted. Its trajectory was slightly off, as if some faint, unseen force were pushing it. At first, scientists thought this might be an error in the data, but when multiple independent teams confirmed the effect, the implications became unavoidable. Something was giving Oumuamua an extra nudge. One natural explanation was outgassing, jets of vapor shooting off the surface like tiny thrusters. This is common in comets, and it can alter their paths slightly. But in Oumuamua's case, there was no visible gas or dust, and the push seemed unusually strong for something invisible. The mystery deepened. If it was a comet, it was unlike any comet we'd ever known. If it was an asteroid, it was behaving like no asteroid ever had. By now, the theories were multiplying. Some astronomers thought it might be made of exotic ices, like pure hydrogen or nitrogen, which could evaporate without leaving visible traces. Others proposed it was a fragment from the surface of a Pluto-like exoplanet, blasted into space by some ancient collision. And then, of course, came the most headline-grabbing idea that it might not be natural at all. Harvard astronomer Avi Loeb and his colleague Shmuel Bialy published a provocative paper suggesting Oumuamua could be an artificial object, a thin, light sail-like structure sent intentionally or accidentally by another civilization. They pointed to its strange shape, its unexplained acceleration, and its lack of a cometary tail as clues. Perhaps it was a derelict probe, drifting through space after countless millennia. Or maybe it was debris, space junk, from some ancient alien technology long since abandoned. The mainstream scientific community was cautious, even skeptical, about such claims. Extraordinary ideas require extraordinary evidence, and Oumuamua was fading too fast to give us that kind of proof. Still, the alien probe hypothesis exploded in the public imagination, and for months the object was at the center of one of the most fascinating debates in modern astronomy. Was Oumuamua a natural shard of interstellar rock, a frozen, invisible comet, or the silent relic of something far more advanced? By December 2017, the visitor was already too faint for even Hubble to track. We had just 11 short days of high-quality observations, an eye blink in astronomical terms, to make sense of it. The data we gathered was enough to write dozens of scientific papers, yet still too little to answer the central question: what was Oumuamua, really? In the end, it slipped away into the black, heading toward the constellation Pegasus, where it will drift forever, or at least until it crosses paths with another unsuspecting star system millions of years from now. We may never see it again, but its visit changed something fundamental. It made the galaxy feel less distant, less abstract. For the first time in history, humanity had watched a messenger from another star pass through our skies, even if we couldn't quite understand what it was trying to say. Oumuamua's departure left a strange emptiness, not just in the sky, but in the minds of those who had tried to understand it. For astronomers, this was like finding a message in a bottle washed ashore, only to have the tide snatch it away before they could read the whole note. But the brief encounter had taught them something important. Interstellar visitors were real, and they might pass through our solar system more often than anyone had dared to hope. You see, before 2017, the idea of spotting such an object was almost considered science fiction. The distances between stars are so vast, and the space between them so empty, that the odds seemed nearly impossible. Yes, astronomers believed stray chunks of rock and ice must wander the galaxy after being ejected from their home systems, but no one expected to actually see one. That changed the moment Oumuamua appeared and then vanished, reminding scientists that the universe was still capable of genuine surprises. In the weeks following its discovery, researchers began rethinking their estimates. If we had managed to spot Oumuamua with a telescope that only scanned a small part of the sky, that meant there could be countless others slipping past unnoticed. They might be large or small, fast or slow, icy or rocky, but they were out there, moving silently through the darkness, each with its own ancient story. The realization created a ripple effect. Astronomers began pushing for new sky surveys with more powerful, faster scanning telescopes. The most promising of these was the Vera C. Rubin Observatory in Chile, still under construction at the time. Its massive, wide-field camera would soon be able to scan the entire visible sky every few nights, making it far more likely to catch the next interstellar visitor before it was already speeding away. But Oumuamua didn't just inspire new instruments, it also inspired new dreams. What if, next time, we were ready? What if we could launch a spacecraft to intercept one of these objects while it was still inbound, before it sped past and vanished into the void? That's no small challenge. Interstellar visitors move at incredible speeds, and catching one would require a rapid response mission unlike anything humanity has attempted before. Some space agencies and private groups began to sketch out ideas. Could we have a ready-to-go spacecraft waiting on standby, fueled and prepared to launch at a moment's notice? Could new propulsion methods, like solar sails or nuclear drives, give us the speed we'd need to chase an object that might be traveling over 300,000 kilometers per hour? The engineering problems were huge, but so was the motivation. This wasn't just about exploration. It was about making sure we didn't miss our next chance to examine something truly alien, whether natural or artificial, up close. And for the public, the story of Oumuamua tapped into something even deeper. It stirred that ancient curiosity about the unknown. Was this just an oddly shaped piece of cosmic debris, flung from a distant star system in some long-forgotten collision? Or had we, in our cosmic infancy, just witnessed a relic of an intelligence far older than our own? That question, however unlikely the alien explanation might be, kept Oumuamua alive in the headlines, in books, and in late-night conversations long after it had faded from sight. For many scientists, though, the real legacy of Oumuamua wasn't about proving aliens existed or didn't exist. It was about humility. It reminded us that the universe is not a closed book. It's still being written, on a scale so large and in a language so strange that we've only begun to sound out the words. Somewhere out there, beyond the thin shell of light that marks the edge of our solar system, Oumuamua keeps tumbling. It carries no radio signal, no clear message, only the silent testimony of its existence. And whether it came from a chaotic birth in some alien asteroid belt or the long-lost workshop of a civilization we'll never know, it left us with a simple truth. The stars are not as empty as they seem. The next time a messenger arrives, we might be ready to meet it halfway. And maybe, just maybe, we'll learn the story it's been carrying for millions of years. While the mystery of Oumuamua still hung in the air, astronomers didn't have to wait long for the universe to send another surprise. Less than 2 years later, in August 2019, an amateur astronomer named Gennady Borisov, observing from his personal observatory in Crimea, spotted a new faint blur in the sky. At first, it looked like a regular comet, nothing unusual, but when its orbit was calculated, the numbers jumped off the page. Its path was hyperbolic, just like Oumuamua's. This object, later named 2I Borisov, the 2I marking it as the second officially recognized interstellar object after Oumuamua, was another traveler from beyond our solar system. But unlike its predecessor, Borisov looked much more like what scientists had expected from an interstellar visitor. It had a visible tail, a coma of dust and gas, and a composition similar to comets from our own Oort cloud. In many ways, Borisov was the control sample scientists had been hoping for. If Oumuamua was strange and ambiguous, Borisov was familiar and textbook, proof that other star systems form icy, dusty comets much like ours. It also confirmed something else. Interstellar objects weren't once-in-a-lifetime encounters. We had now seen 2 in just over 2 years, suggesting they might be fairly common, even if most were too faint or too far for us to detect. But there was one big difference between the two. Oumuamua had been spotted after its closest approach to the Sun, meaning it was already on its way out before telescopes caught it. Borisov, on the other hand, was discovered early enough for astronomers to watch it for months as it swooped around the Sun. This gave them a much better look at its physical makeup. Spectral analysis revealed that Borisov was rich in carbon monoxide ice, far more than most comets in our solar system. This hinted that it had formed in an extremely cold environment, perhaps in the far reaches of its home star's icy outskirts. That kind of chemical fingerprint was like a cosmic passport stamp, giving clues about where in the galaxy it might have been born. For many scientists, the arrival of Borisov confirmed the theory that our galaxy is full of wandering debris, objects knocked loose from their home systems by gravitational chaos and set adrift between the stars. Over time, these interstellar travelers might pass through dozens of different star systems, each encounter altering their path just a little more. In a way, Borisov was like a dusty hitchhiker on a billion-year journey. Still, while Borisov was scientifically valuable, it didn't inspire quite the same fevered speculation that Oumuamua had. There was no unexplained acceleration, no unusual shape, no "maybe it's an alien probe" headlines. But that didn't make it boring. On the contrary, having both Oumuamua and Borisov in our records gave scientists a crucial comparison. One object was baffling and possibly unique. The other was familiar and reassuringly comet-like. Together, they painted a more complete picture of the kinds of visitors our solar system might expect in the future. And the future was the most tantalizing part. If we'd seen 2 interstellar objects in such quick succession, how many had we missed in centuries past? How many had slipped through before we had the technology to spot them? And how soon before the next one came along? Something we could perhaps study up close or even meet with a spacecraft. By late 2019, talk of an interstellar object watch was becoming serious. Astronomers envisioned a global network of telescopes dedicated to spotting these fleeting visitors as early as possible. The sooner they could be found, the more time there would be to prepare for observation, or maybe even an interception. Borisov eventually broke apart in mid-2020, its icy nucleus crumbling under the stress of its sunside pass. By then, however, it had already given us months of data, enough to study for years to come. And while its visit ended in dust, its significance lingered. It had proven that interstellar visitors could be caught early, tracked for long periods, and analyzed in detail. The lesson was clear. Oumuamua had been our mysterious hello, Borisov, our patient conversation. The next time the galaxy sent a guest our way, we'd be ready to offer more than just a wave as it passed. By the time Borisov faded from view in 2020, the astronomical community was more certain than ever that interstellar visitors were not rare flukes. They were a natural part of the galaxy's traffic. The question now was not if another one would come, but when, and more importantly, how prepared we would be when it happened. The challenge, however, was speed. These objects do not saunter into the solar system, they sprint. Oumuamua moved at over 87 kilometers per second relative to the Sun. Borisov was not far behind. By the time Earth's telescopes spot them, they are often already deep within the inner solar system, leaving only weeks, or at best months, before they vanish into the dark again. This speed problem sparked a flurry of proposals. One of the most ambitious was something called the ready-to-launch interceptor concept. The idea was deceptively simple. Instead of designing a new spacecraft every time a visitor appeared, why not have one, or even several, already built, fueled, and waiting in orbit? The moment a target was spotted, the spacecraft could launch or fire its engines, racing to meet the intruder before it escaped. Of course, nothing in space is ever simple. Building a probe capable of chasing such fast-moving objects meant considering propulsion technologies far beyond the slow, chemical rockets we usually send to planets. Concepts like solar sails, giant, ultra-thin sheets pushed by sunlight, came back into the spotlight. Nuclear-powered engines, laser-pushed sails, and ion drives were also discussed. The European Space Agency even began studying a mission called Comet Interceptor, set to launch in 2029. Its main goal wasn't specifically interstellar objects. It would wait in space for any cometary visitor that hadn't been studied up close before, but many scientists saw it as a perfect test run for meeting a future alien wanderer. Meanwhile, the Vera C. Rubin Observatory, mentioned in the wake of Oumuamua, was steadily approaching completion in Chile. With its ability to scan the entire southern sky every few nights, Rubin was expected to be a game changer. It could detect faint, fast-moving objects earlier than any previous survey, potentially spotting an interstellar traveler months or even a year before closest approach. And yet, alongside the technical discussions, there was a quieter, almost philosophical shift happening. Oumuamua had reminded us that not all mysteries come in the form of distant galaxies or black holes. Some arrive in our own cosmic backyard. Borisov had shown that these visitors could be scientifically rich without being exotic. Together, they had opened a new frontier: interstellar archaeology, the study of ancient wandering debris from other star systems. This was a tantalizing idea because, unlike distant exoplanets, which we can only study indirectly, interstellar objects are physical pieces of other solar systems coming straight to us. A grain of dust from Borisov might have formed around a star that no longer exists. A fragment from an Oumuamua-like object could hold materials forged in the heart of a long-dead supernova. In essence, the galaxy was delivering samples for free. It was up to us to grab them. By the early 2020s, the idea of capturing an interstellar object wasn't just a dream. It was entering serious engineering conversations. Could we design a net-like spacecraft to scoop up particles from a passing comet's tail? Could we send a swarm of small probes to surround an incoming visitor, photographing and scanning it from all angles? Could we, in the far future, actually land on one? Each possibility carried challenges, but also a sense of urgency. The next object could be icy, rocky, metallic, or something no one had imagined. It could be harmless, or it could tell a story that reshapes how we see life's possibilities in the galaxy. And unlike stars or planets, these visitors give us no second chances. We only get one shot before they are gone forever. That reality was both a frustration and a thrill. It meant that somewhere, maybe right now, the next messenger was already speeding through the void toward us, silent, unknowing, and completely unaware that it was about to become the most talked-about object in the solar system. If Oumuamua and Borisov were the opening chapters in our story of interstellar visitors, then the years that followed became the slow, tense pause before the next act. Astronomers knew the next object could appear at any moment, and in the meantime, they began sharpening the tools they would use to catch it. One of the most important developments came not from a telescope, but from data science. Traditionally, spotting objects in the sky involved looking for faint dots of light that moved between images taken hours or days apart. This worked well for asteroids and comets, but interstellar objects posed a special problem. They move in unusual paths that don't match the orbits of anything bound to our sun. To address this, teams began developing AI-powered search algorithms. These systems could sift through enormous amounts of telescope data in real time, flagging anything that looked suspicious, anything that wasn't following the slow, looping dance of normal solar system bodies. The hope was that these algorithms could spot an incoming visitor weeks earlier than human observers could. The Vera C. Rubin Observatory was central to this plan. Its massive 8.4-meter mirror and ultra-wide camera would scan the entire southern sky every 3 nights, producing more data in 1 year than all previous sky surveys combined. That much information was impossible for humans to process manually, but perfect for AI to comb through, hunting for faint, fast-moving streaks that might be the next Oumuamua. But detection was only one half of the race. The other was interception. Here, ideas were starting to leave the drawing board. NASA researchers revived a concept they called the cryogenic NEO interceptor, a spacecraft preloaded with fuel, sitting in deep space near Earth, able to launch at short notice to chase down fast-moving objects. If the target turned out to be interstellar, the interceptor could swing past it, taking images and spectra up close. Other teams dreamed bigger. What if we didn't just fly by? What if we matched speeds and stayed alongside the object for days, weeks, or even months? This would let us watch its surface in detail, see how it changed as it approached and left the sun, and maybe even deploy small landers. The Breakthrough Starshot initiative, best known for its idea of sending laser-driven microprobes to another star, offered an intriguing side project, adapting its ultra-light, ultra-fast sail technology for chasing interstellar visitors. A sail probe could, in theory, accelerate quickly enough to catch up to even the fastest incoming traveler. All of this preparation carried a subtle undercurrent of excitement, because the next visitor might not just be scientifically interesting, it might be unlike anything we've ever seen. Consider the possibilities. It could be a giant, icy relic from the frozen edge of a young star system, untouched for billions of years. It could be a shard of planetary crust blasted away when a world was shattered by a collision. It could be a chunk of metal, a fragment of a core from a planet that never finished forming. And, in the most speculative scenario, it could be artificial, built by intelligence somewhere out there. This last idea was rarely voiced in official research papers, but it remained in the background of public curiosity. Oumuamua had cracked open that door, and while most scientists leaned toward natural explanations, the fact remained: if alien civilizations exist, sending out long-lived probes to explore other star systems is exactly the kind of thing they might do. And so, the watch continued. Every clear night, telescopes scanned the skies. Every morning, computer systems processed terabytes of data. The next visitor could be days, months, or years away. But when it came, astronomers were determined to be ready. Somewhere in the cold and silent gulf between the stars, another wanderer was already on its way. It didn't know it was heading toward a world full of telescopes, radio dishes, and curious minds. It didn't know it was about to become a celebrity. But when it arrived, it would carry with it a message, whether of ice, rock, dust, or something far stranger, that would remind us once again that we live in a galaxy filled with travelers. By the mid-2020s, the race to meet the next interstellar visitor was becoming more than an astronomer's dream. It was evolving into a global coordination effort. Agencies in the United States, Europe, China, and Japan began discussing how to work together when the next Oumuamua moment happened. The reason was simple. No single telescope or space agency could handle the challenge alone. The key to this coordination was time. With Oumuamua, astronomers had only 11 days of good observing before it became too faint for most telescopes to track. With Borisov, they had just a few months. For an actual spacecraft mission, that was nowhere near enough. To make things worse, once an interstellar object is spotted, its precise trajectory must be calculated quickly, sometimes within days, if we're to know whether we can reach it at all. This is where the Planetary Defense Coordination Office, yes, the same group responsible for tracking hazardous asteroids, stepped in. Their job wasn't just to protect Earth from collisions, but also to identify unusual objects entering the solar system. Now, part of that work involved preparing for fast international alerts. The moment a candidate interstellar object was found, observatories worldwide would be notified, ensuring 24/7 tracking. But there was another layer of excitement: sample return missions. Imagine it, sending a probe to intercept an interstellar comet, scoop up a small amount of dust or ice, and bring it back to Earth. That tiny package could contain material from a planetary system we've never seen, molecules that formed under alien suns, perhaps even prebiotic building blocks of life. The concept wasn't science fiction. NASA's OSIRIS-REx had already proven it was possible to grab material from a small body, asteroid Bennu, and return it safely. Japan's Hayabusa missions had done the same with even smaller asteroids. Scaling this technology to interstellar speeds would be difficult, but not impossible. Some scientists even suggested a grab-and-go spacecraft, a small, fast, highly maneuverable probe that could survive a high-speed pass through an object's dusty coma, catching particles in an aerogel trap. The key would be precision timing. Missing the object by even a few seconds could mean returning home empty-handed. Meanwhile, computer simulations were revealing something surprising. The solar system might be full of captured interstellar objects, bodies that had wandered in and, through rare gravitational interactions, become trapped in orbits around the Sun. These would be much easier to reach than a high-speed flyby, and they might already be hiding among the asteroids and comets we know. If we could find one, it could become humanity's first permanent interstellar visitor, waiting patiently for us to study it. Beyond the practical challenges, there was a sense that this effort touched something deeply human. For most of history, we've looked up at the stars and wondered what lies between them. Now, the galaxy was sending small pieces of itself straight to our doorstep. We didn't have to cross the void to touch another solar system. It was crossing the void to touch us. Every night, astronomers reminded themselves of a sobering truth. When the next object comes, there will be no second chance. If we fail to track it, if we fail to study it, it will disappear into the darkness forever, taking with it secrets we may never hear again. And somewhere out there, beyond Neptune's cold shadow, that next wanderer might already be bending its path toward the Sun. Silent, invisible, but coming. In early 2028, a faint streak appeared in the nightly images from the Vera C. Rubin Observatory. At first, it was just another possible moving object in a list of hundreds. The AI flagged it because its motion didn't fit any known asteroid orbit. By the time the morning shift arrived, the system had already compared its path to every object in the Minor Planet Center's database and come up empty. Within hours, astronomers at observatories in Hawaii, Chile, and South Africa were following up. The results were electrifying. The object was moving too fast to be bound to the Sun. Its incoming speed suggested it came from deep interstellar space. They named it ISO 3, the third confirmed interstellar object, after Oumuamua and Borisov. Unlike the first two, this one had been spotted 2 years before its closest approach to the Sun, an eternity in interstellar object terms. That lead time meant humanity had something it had never had before: a chance to meet the visitor up close, in person, with a spacecraft. Space agencies scrambled into action. The cryogenic NEO interceptor, which had been waiting in a ready orbit near Earth, was powered up and given new navigation instructions. Mission planners worked around the clock, calculating the optimal path to rendezvous with ISO 3 months before it reached perihelion. Even as the spacecraft began preparing to launch, telescopes were feeding scientists a steady stream of new data. This object wasn't just interesting, it was weird. Its spectrum showed deep absorption lines that didn't match common solar system ices or minerals. Some thought it was rich in exotic carbon compounds. Others whispered, carefully, away from press microphones, that the patterns looked engineered. The press, of course, ran wild. Headlines blared, "Alien probe incoming," and scientists raced to meet possible visitor from another civilization. Most astronomers rolled their eyes. Caution was vital. But they also admitted privately that ISO-3 was behaving unlike any comet or asteroid they had studied before. Meanwhile, in mission control rooms across the world, engineers were wrestling with the harsh reality of interstellar chasers. ISO-3 was moving at nearly 45 kilometers per second relative to the Sun. Even with the interceptor's powerful ion drives, catching it would be like trying to hop onto a train while standing on a motorcycle going the opposite direction. The plan they settled on was bold. Rather than matching speeds completely, the spacecraft would perform a high-speed intercept, passing within a few hundred kilometers of the object, while firing off a swarm of mini-probes. Each mini-probe would carry cameras, spectrometers, and dust collectors, transmitting their data back to the main craft before being left behind. By late summer, the interceptor was on its way. The clock was ticking. Every day of delay meant ISO-3 was further away, and every kilometer per second of relative speed made the flyby harder. But for the first time in history, humanity was in position not just to see an interstellar visitor as a faint dot in the sky, but to meet it in the dark. Back on Earth, telescopes continued to watch, and something unusual began to happen. The object's brightness fluctuated in a regular pattern, bright, dim, every 16 hours. It could have been rotation, it could have been surface features, but some couldn't shake the thought. It looked like a signal. And so, as ISO-3 sped toward the inner solar system, the story began to shift from a purely scientific mission to one tinged with the possibility of first contact. By autumn of 2028, ISO-3 was no longer just an astronomical curiosity. It had become a worldwide obsession. Social media feeds overflowed with artists' impressions. Some showed a jagged comet-like body streaking through the black, while others dared to depict gleaming alien machinery drifting silently toward the sun. News channels devoted entire segments to the visitor, as they called it, complete with countdown clocks to the moment of spacecraft intercept. In universities and research labs, however, the atmosphere was more focused and more tense. The 16-hour brightness cycle was being scrutinized to exhaustion. The pattern was too perfect for many scientists' liking. Rotating asteroids usually had irregular light curves, small bumps and dips caused by uneven shapes and surfaces. ISO-3's curve was eerily smooth, almost as if its reflectivity were controlled. Radio telescopes began beaming focused signals toward it, simple pulses, encoded messages, even mathematical sequences. Weeks passed and nothing came back. That didn't mean much. The object was still far away and small, and if it wasn't trying to talk to us, we might never hear a thing. But the possibility of intelligence remained the elephant in the room. Meanwhile, the cryogenic Neo-interceptor, now universally referred to as the Chaser, was in the middle of its most delicate maneuvers. In order to meet ISO-3, it had to execute a risky gravity assist around Venus, skimming just 250 kilometers above the planet's cloud tops. The heat shield endured temperatures hotter than molten lead, while the ion engines prepared for their final long burn. Every system was performing flawlessly, but engineers knew that one wrong calculation could leave the spacecraft sailing forever into deep space. The plan for the intercept was now finalized. 1. Main craft flyby. The Chaser would pass within 200 kilometers of ISO-3 at a closing speed of over 50 kilometers per second. 2. Mini probe swarm. A dozen suitcase-sized probes would be deployed minutes before the flyby, fanning out to capture high-resolution imagery and collect dust and gas samples. 3. Return capsule. 2 probes were fitted with small, heat-shielded capsules to return samples to Earth within 5 years, if they survived the violent collection process. For weeks, scientists had been arguing about what they might see. If ISO-3 was a natural body, it could teach us about the raw materials of alien planetary systems, different isotopes, unfamiliar organic compounds, maybe even clues to how life could begin in other parts of the galaxy. If it was artificial, well, that would change everything. But even if it was built, by whom? And why was it here? As December approached, the object grew brighter in the sky. Amateur astronomers with backyard telescopes could now find it, a faint moving speck among the stars. Its light curve continued to repeat like clockwork. And yet, in the last few cycles, subtle changes appeared. Tiny shifts in the timing, like a pendulum swinging slightly off beat. Theories exploded online. It was adjusting its spin. It had noticed us. It was preparing for something. The chaser had less than 40 days to arrival. The final trajectory corrections were being planned. Mission control rooms were full of coffee cups, glowing monitors, and engineers sleeping in corners between shifts. Every hour, they checked and rechecked the numbers, knowing that if they missed their target by even a fraction of a second, ISO 3 would slip away into the dark forever. And then, 3 weeks before intercept, a faint, narrow-band radio signal was detected, coming not from Earth, not from any known satellite, but from somewhere in the exact direction of ISO 3. It lasted just 82 seconds. The moment the 82-second signal hit the data logs, the radio astronomy team at the Deep Space Network knew they had something unusual. It wasn't background noise. It wasn't the hiss of the cosmic microwave background or the erratic crackle of solar interference. This was structured. The waveform looked clean, sharp, and unnaturally regular, like the heartbeat of a machine. It repeated a short, simple pattern. 3 pulses, pause, 5 pulses, pause, 3 pulses, then silence. The signal didn't come back. Within minutes, every major observatory capable of listening at that frequency was turned toward ISO 3. But whatever had spoken, if it was speaking, had gone quiet again. The official statement from the International Astronomical Union was cautious. The origin of the signal is unknown. While its direction aligns with ISO 3, further observation is needed before any conclusions can be drawn. Unofficially, the debate was already raging. Some scientists believed it was nothing more than a strange natural phenomenon, perhaps solar wind interacting with metallic elements on the object's surface. Others whispered that the sequence 3, 5, 3 couldn't be random. Prime numbers were rare in nature. They often appeared in human attempts to communicate mathematically. In the middle of the frenzy, the cryogenic NEO interceptor team faced a choice. Option A, stick to the original high-speed flyby plan, which was safe for the spacecraft, but left no room for slowing down or extended observation. Option B, burn extra fuel to reduce the closing speed slightly, giving the probes a better chance to collect data, but at the risk of missing ISO 3 entirely if calculations were off. After 3 tense days of simulations and late-night arguments, they chose option B. It was a gamble, but no one wanted to pass this close to something potentially artificial without wringing every possible moment out of the encounter. Meanwhile, more telescopes joined the hunt for follow-up signals. In the second week of listening, a faint echo appeared, not in radio, but in laser wavelengths. A brief flash of green light, perfectly collimated, lasting less than a millisecond, was detected by 2 independent observatories. Again, the source lined up with ISO 3's location. If the object was trying to communicate, the messages were erratic, short, and possibly aimed at someone or something else entirely. The chaser was now less than 20 days from intercept. The object's light curve had grown stranger still. The 16-hour cycle was breaking down, replaced by unpredictable flickers and sudden flares. One particularly bright flash blinded sensors for nearly a full second, something no one had seen before. At a press conference in Geneva, the lead scientist on the mission, Dr. Miriam Sayegh, was asked the question everyone had been dancing around for months. Do you think it's a spacecraft? Her answer was measured, but her eyes betrayed the tension. We don't know yet, but if it is, we're about to find out. Behind the scenes, contingency plans were drawn up. The mini-probes' sampling arms were reprogrammed to prioritize contact with any non-natural surface. Imaging software was adjusted for high-contrast edges, just in case they were photographing something with sharp lines or geometric symmetry. And then, just 5 days before intercept, ISO 3 did something no natural object had ever been seen to do. It changed course. The change in ISO 3's course wasn't dramatic, just a subtle, graceful drift. altering its trajectory by less than half a degree. But at the speeds involved, that tiny shift meant a missed distance of thousands of kilometers if the chaser didn't respond. At first, Mission Control thought it was a data error. They ran the orbital calculations again and again until the truth settled in like a cold weight in the room. The numbers were solid. ISO-3 had accelerated on its own. Natural explanations crumbled under scrutiny. Outgassing, jets of vapor from frozen material turning to gas, was the most common culprit for small comets, but ISO-3 showed no visible tail or venting. Its spin rate didn't change in a way consistent with random thrusts, and the timing. The shift came just after the last faint green laser flash. Could be coincidence, someone muttered in the control room. No one believed it. The course correction threw the intercept plan into chaos. Option B, the slower flyby, was suddenly in jeopardy. If they didn't act fast, the spacecraft might pass hundreds of kilometers too far away to get meaningful data. The mission engineers made a gut-wrenching decision: fire the ion engines at maximum for 36 continuous hours, draining almost every gram of xenon propellant they had left. This meant there would be no second chances. The chaser would burn itself into the perfect intercept, and afterward, it would be unable to maneuver again. The entire mission would ride on a single pass. For the next day and a half, the spacecraft obeyed, its thrusters whispering faint blue plasma into the void. On Earth, the world was transfixed. Every news outlet ran constant coverage. Theories grew more extreme. Some said ISO-3 was avoiding us, others that it was meeting us halfway. Then the object's behavior changed again. The once erratic flashes became rhythmic, almost like a beacon. 3 bright pulses, pause, 5, pause, 3. The same as the first radio signal. This time it wasn't 82 seconds. It went on for over an hour. Dr. Sayegh, who hadn't slept more than 2 hours in days, stared at the incoming light curve and whispered, "It's not just a signal, it's a lock-on." As if to confirm her fear or hope, the last brightness cycle before intercept showed something else. Between the pulses, the reflected light had jagged, uneven dips, like sunlight passing over edges that were straight. The first high-resolution images from the chaser's long-range camera trickled in a few hours later. ISO-3 was no shapeless rock. It was elongated, yes, but parts of it were flat and geometric, with repeating angles and panels that caught the sunlight like mirrors. It didn't look built for beauty. It looked built for endurance. And in less than 36 hours, humanity would be close enough to see every detail. 36 hours. That was all the time left before humanity's first close encounter with something that might not be natural. The Chaser spacecraft's systems were now in what Mission Control called encounter mode, a sequence designed for one thing only: maximum data collection in the shortest possible time. Every instrument was powered up. The 2 mini-probes, Scout 1 and Scout 2, were warmed from their deep sleep mode, ready to detach and dive in. Their cameras would be snapping dozens of frames per second. Their laser spectrometers would scan for traces of metals, composites, and organics. And if either probe survived the pass, it would try to transmit directly back to Earth via its tiny antenna. But before any of that, there was the reveal. At 22 hours before intercept, the Chaser's narrow-field camera locked onto ISO-3 again. The image filled in pixel by pixel, slowly sharpening, until the team in Mission Control fell silent. The object was not symmetrical, but it had a deliberate shape, like a shard of something larger. Its longest side gleamed with what looked like ribbed panels, alternating between dull and reflective strips. Some areas were darkened, possibly charred, as though scorched in deep space or by some violent event. And then there was the impossible detail. A circular pattern on one side, not unlike an array of hexagonal tiles, each one the size of a small building. The tiles reflected light in a way that suggested they were still intact. "That's not a rock," whispered one of the imaging specialists. "It's a machine," said another more bluntly. Mission Control didn't officially confirm that, but the images spoke for themselves. 18 hours before intercept, ISO-3 changed behavior yet again. The light pulses stopped. Instead, faint streams of particles, barely detectable, began drifting from the object. They were too slow to be propulsion exhaust, more like a leak or a release. Some scientists suggested it was venting to stabilize its spin. Others thought it might be shedding mass deliberately. Dr. Sayegh had another idea, but she didn't share it aloud. It might be sending something ahead. At 8 hours before intercept, the chaser's sensors picked up 2 tiny blips moving just ahead of the object, no more than a few meters across. They were tumbling slowly, reflecting sunlight in quick flashes. Whatever they were coming into range, and the chaser was on an unchangeable collision course with their path. The team debated whether to adjust trajectory to avoid them, but it was too late. Any course change now would ruin the intercept entirely. They decided to hold steady and watch. 5 hours before intercept, Scout 1 detached and began its programmed dive toward ISO 3, banking to pass just 200 meters above the surface. If it survived, it would collect high-res images and try to scrape a fragment. 2 hours before intercept, Scout 2 followed, aiming lower, close enough to touch the surface with its sampling arm. Mission control fell into a tense, hushed rhythm. Every few minutes, new frames arrived, each one clearer than the last. The flat panels were riddled with scratches and impacts. Some edges were bent outward, as though something inside had once tried to push its way out. Then, just 30 minutes before intercept, Scout 1 sent back the image that froze everyone's blood. In one of the darker sections, a circular opening, perfectly smooth, gaped like the iris of an eye. And from deep within, something reflected the sunlight. Not randomly, but in a quick, deliberate triple flash. 3. Pause. 5. Pause. 3. The same sequence. In less than half an hour, they would be close enough to see inside. The final 30 minutes felt longer than the entire mission combined. Every instrument on the chaser was running at full tilt, transmitting raw streams of data toward Earth. The delay was still over 8 minutes, which meant that what the control room saw was already history. The spacecraft was flying blind into the future. The 2 small tumbling blips ahead of ISO 3 were now resolved into shapes. Irregular, metallic fragments. One looked like a flat plate with evenly spaced holes. The other was a twisted lattice of beams, as if ripped from a larger frame. Both bore the same weathered texture as the panels on the main body. Scout 1 was first to meet them. Its camera caught the moment it passed the flat plate. A close-up that showed not corrosion, but engraving. Not random scratches, but etched grooves that curved and spiraled in a pattern no human alphabet matched. They were shallow, worn, but still deliberate. Mission Control barely had time to react before Scout 1 crossed the next threshold, 300 meters from ISO 3's surface. The images that came through now showed a landscape of alien architecture, fractured panels jutting like cliffs, ribs of dark material running in perfect parallel lines, and gaps between them that sank into pure black. Then came the iris. From a distance, it had looked like a circle of darkness. Now, at close range, Scout 1's camera showed detail. The opening was ringed with hexagonal plates, each aligned with impossible precision, their edges beveled inwards. In the very center, barely visible, was a faint shimmer, as if something just beyond the opening caught and bent the sunlight into liquid gold. It flashed. 3. Pause. 5. Pause. 3. Brighter now, so bright the camera's sensors nearly saturated. Scout 1 was gone seconds later, not destroyed in a dramatic explosion, just silent. No more telemetry, no more images, as though it had flown into a dead zone where signals could never escape. The chaser pressed on. Scout 2 took the lower pass. Its sampling arm extended. It skimmed just meters above the surface. One brush against the panel's edge was enough to grind away a few specks. Samples that, if they survived re-entry to Earth, might answer questions humanity had asked for centuries. Then it happened. ISO 3 moved. Not a slow drift, not a natural tumble. It tilted. The massive shard rotated, exposing more of the hexagonal opening toward the chaser. The gold shimmer swelled, no longer faint but blazing, a beam, narrow yet sharp, slicing across the black. The beam didn't hit the chaser, it passed just ahead, like a lighthouse sweep. But every sensor spiked. Every instrument read noise, and for 3 full seconds, the spacecraft's systems froze. When they recovered, the chaser was less than 5 kilometers from the surface. The final high-resolution images were already streaming toward Earth. The hexagonal tiles were not uniform. Some were missing, revealing a lattice beneath. The shimmer was not light, but a fluid, metallic curtain, rippling as if stirred by an unseen wind. And behind that curtain, shapes. Not clearly visible, but silhouettes that hinted at depth, structure, and scale far greater than the shard's exterior suggested. The chaser passed the far edge of ISO 3 and began to drift away, its xenon propellant exhausted, its trajectory now carrying it into the deep dark. 8 minutes later, in the control room, the last image arrived. It was unlike the others. Not sharp, not clear. But in the golden shimmer, for a fraction of a second, a darker form had stood against the light. Tall, narrow, unmistakably vertical. And it was facing the camera. The launch was never publicly announced. Officially, the new spacecraft was a high-speed probe to study distant icy bodies in the outer solar system. In reality, its mission patch, never shown to the public, featured 3 simple symbols: a hexagon, a golden wave, and a point of light in a black field. By the time it departed, ISO 3 was long gone, carried into the dark beyond Neptune's orbit. But the coordinates hidden in its signal had burned into the minds of those who saw them. The location was fixed, unchanging, as if whatever was there was waiting for someone or something to arrive. The probe's design was unlike anything launched before. It carried no weapons, but it was armored against high-velocity debris. It had cameras capable of tracking objects smaller than a coin at thousands of kilometers. Its main transmitter had enough power to scream across half the galaxy. Still, the deeper innovation was hidden inside. An experimental quantum entanglement communicator. It wasn't fast enough to bypass physics completely, but it could send a single bit of data instantly, yes or no, without waiting years for radio waves to cross space. The mission team called it the Lifeline. 17 months after launch, the probe slipped beyond the orbits of Pluto and Eris. Solar power was useless here. Everything ran on a compact reactor. Then, on the 521st day of the mission, it entered the coordinate zone. There was no drifting shard like ISO 3 this time. Instead, the instruments registered a perfect sphere, exactly 3 kilometers in diameter, hovering motionless among the comets. Its surface was flawless black, reflecting nothing, swallowing even the faint starlight around it. As the probe approached, the sphere opened. Not slowly, not like a door, but in an instant, an iris of hexagonal plates peeling back to reveal the same golden fluid curtain. And in the center of that curtain, something was already moving forward. The quantum communicator's single bit pulsed back to Earth. It was yes. The yes bit was enough to throw the control room on Earth into chaos. The team knew that the probe's autonomous systems were in charge now. No one could steer it. No one could warn it to retreat. It was on rails, locked into a slow approach toward the sphere's open heart. Inside that golden fluid curtain, movement resolved into form. Not the strange branching silhouette seen inside ISO 3, but something sharper, more deliberate. 3 long, articulated limbs emerged first, each ending in a curved structure, neither claw nor hand, but something in between, like tools shaped for a task unknown to humans. Behind them came the body, smooth, seamless, and jointed in ways that made no sense for life as Earth knew it. The material wasn't metal in the usual sense. It shifted subtly, like a living thing adapting to light and shadow. Then the head, if it could be called that, tilted toward the probe. It didn't have eyes, not in any recognizable way. Instead, its surface rippled, and patches of the same hexagonal tiling seen on ISO 3 appeared. shifting as though adjusting a lens. For the briefest moment, the probe's cameras saw its own reflection. Tiny, fragile, a speck of human technology in the void. That's when the signal began. Not radio, not laser. Something else. Pulses across multiple wavelengths, layered and recursive, impossible to decipher in real time. The probe's AI dumped every byte into storage, compressing until its memory was nearly full. But it also triggered the lifeline, sending a second and final instant bit to Earth. This one wasn't yes or no, it was ready. Back in the sphere, the golden fluid surged forward, surrounding the probe without touching it. The alien figure stepped back into the shimmering veil, its limbs folding inward, and then, like a breath being drawn, the plates of the sphere closed again. The probe's signal stopped, and 6.8 billion kilometers away, on a quiet night in mission control, the word "ready" blinked once on a secure screen, and stayed there. The word "ready" stayed on the secure channel for 12 minutes before anyone spoke. In the main control room, the hum of cooling fans and the faint tapping of keyboards were the only sounds. No one wanted to be the first to break the silence, because everyone understood the same thing. This wasn't a mission update. It was an invitation. Dr. Sayegh finally stood, pushing back her chair. "We have two possibilities," she said, voice low but steady. "Either they're expecting us to send another probe, or they're expecting us." The debate began immediately. Politicians wanted control. Militaries wanted preparation. Scientists wanted to send everything, data, greetings, mathematical proofs, into the void. But the most chilling suggestion came from an old systems engineer, a man who had been in the room during the ISO-3 encounter. "They didn't just send coordinates," he said. "They sent a test. ISO-3 was the bait, the sphere was the doorway. Now they've told us they're ready for the real meeting." For weeks, the argument stretched across time zones and governments. Should humanity go? Could humanity go? And if it did, who would speak for an entire species? Meanwhile, the data from the alien signal was slowly, painfully decoded. Most of it was still a mystery, but one part was unmistakable. A repeating pattern of planetary alignments, including Earth, Jupiter, and Neptune, all converging on a single future date. It was just over 9 years away. That meant one thing. If humans wanted to meet them at the Oort cloud, they would need to start building the ship now. In a sealed hangar, under floodlights and guarded by silence, the first structural ring of the interstellar vessel was laid down. No flags, no national markings, only a designation stamped into the metal in small, precise letters. AM1, Ambassador 1. The countdown had begun. The room was quiet now. No flashing alarms, no urgent voices on the comms, just the slow awareness that the next move was humanity's to make. Outside the building, the night sky was clear. Above them, billions of stars burned silently, as they had for millennia. Somewhere far out there, beyond Pluto, beyond the scattered icy rocks of the Kuiper Belt, the sphere waited, still, patient, unchanging. The word "ready" remained in the archives, preserved in 100 backups. It was small, almost insignificant, a single signal buried in the noise of the universe. And yet, to those who had seen it arrive, it meant more than any spacecraft, more than any flag planted on any world. It meant someone was listening. It meant the long loneliness of the cosmos might one day end. In the months that followed, work on Ambassador 1 would move in quiet stages. Metal taking shape, reactors humming for the first time, navigation arrays aligning to distant pulsars. But here, in this moment, the world could breathe. There was still time before the meeting, still time before the journey. The stars outside were no closer than they had been yesterday. But now, when people looked up, they could imagine, not just cold, empty distances, but a destination. Somewhere in the dark, someone had opened a door. And for the first time in history, humanity was preparing to step through it. When the lights dimmed in mission control, Dr. Sayegh lingered for a moment, eyes on the ceiling as if she could see through the concrete to the sky. Then she whispered a truth that had been growing in her mind ever since ISO 3 was found. We were never alone. We were just waiting for the invitation.